Hello all, I'm Kostas Ferles, I'm the CTO at Veridise, and I'm joined by Alexander Hicks from Ethereum Foundation, who leads the ZK-VM Verification Initiative, and we're going to talk about that project today. Welcome, Alex.
Thank you for having me.
Let's start with the Ethereum Foundation's security initiative for ZK-VMs. What are the overall goals of the project?
So I think there are two things. One is obviously we see ZK-VMs as critical to the future development of the layer one, particularly when it comes to scaling, right? So at the moment we're doing re-execution, we have a sense that we can't increase the gas limit, infinitely by doing re-execution, because at some point it won't be possible for all of the nodes to need to re-execute, every block to do so. And so we'd like to transition to having ZK-VMs where you prove the correctness of an Ethereum block in the state transition, and then just verify the proof, which is much easier to do, and you can do it on a Raspberry Pi or a very constrained device, despite the fact that the proofs themselves are going to be kind of these big machines. And so because of that, and because of the complexity of ZK-VMs, then obviously it becomes quite crucial to check that, we're not introducing a lot of complexity and a lot of security issues alongside that. And I think, as many people know, if you have a soundness bug, in a ZK-VM, then obviously you can, kind of submit proofs of false statements. That can mean loss of funds, which is obviously the worst case scenario. But also if you have, kind of a completeness bug, maybe you have a liveness issue. So the Ethereum chain has never gone down. We don't plan on having it go down. And so we want to make sure that we're not losing any robustness guarantees that people have come to expect from the layer one. And that if anything else, we're hopefully making things even more secure by trying to formally verify these ZK-VMs and, also the guest program running on the ZK-VMs, and essentially allow us to improve the performance and scalability of the chain. So the main goal is still improve the performance, improve scalability for the chain, and scaling to handle even more users and even more transactions and onboarding more institutions and more use cases and all of this. But to do that, we obviously need to guarantee security, which is a kind of fairly key property of the layer one.
Oh, that's great. Yeah, these are excellent goals. And maybe can we go in a little bit of what's the progress so far and what lies ahead?
Yeah. So the project is more or less divided into 3 tracks. And the 3 tracks are, I think, hopefully fairly explanatory. So the first track is the ZK-VM track, which focuses on the actual security of the ZK-VM itself, in particular the circuits. The second track is the EVM track, which is the guest program that we want to run on these ZK-VMs. And then the third track is the cryptography track, which concerns itself with the actual proof systems and specifications for these proof systems that people are going to use in tandem with or as part of the ZK-VMs. So progress has been going on all 3 tracks. Progress has been pretty good so far. Now, if we start with the ZK-VM track and we start looking at the security of the circuits, then we've seen a lot of success. Obviously, we've seen S&P solver-based tools like Picus and whatnot being applied to several circuits, in RISC-0, in Succinct. And obviously this is kind of Veridise and not handled on the F side, but it's also nice to see that. But we've had a couple milestones recently, which I think are really worth mentioning, and this is that obviously we're able now to formally verify a RISC-V circuit against the official RISC-V specification that's originally written in a language called SAIL, which is a language to specify hardware ISAs, and so it has RISC-V. It also has some ARM specifications and other ones, and so that's quite nice. So we can show that the constraints for the RISC-V chips all actually kind of match those of the semantics of the SAIL specification that's been extracted to lean, and so we can have good high confidence in our RISC-V chips. Another important thing I think to mention here is that we've also made progress in making this as fast and efficient as possible. So I think probably maybe a couple months ago, you were seeing, things that were quoted at this would take a couple months, this would take, kind of several hundreds of thousands of dollars to do. This has come down now to maybe taking, maybe 10 weeks by one expert engineer to do the proofs. And I'm pretty confident we'll get it down to less than a month, I think, in the next couple of weeks. Simply, we have a simplified hand-polished RISC-V specification that has been shown equivalent to the reference SAIL specification, and that handwritten, nicely polished one is completely bit blastable. So that should make a lot of proofs much, much smoother. Because this blasting is just, really nice and fun and automatic. So that's been, obviously one one, I think, very key milestone has come out in the last couple of months. And so I expect we'll have all of the ZK-VMs, which are candidates for the L1, should have, the RISC-V circuits formally verified, well ahead of actually using ZK-VMs on the L1 suddenly for mandatory proofs. But even at the point where we optionally use them, we should be good with that. So that's been one key goal that we've managed to solve. Now we also have a lot of precompiles to worry about, and maybe some of them might even be potentially even more worrying than the RISC-V circuits. Obviously, with these precompiles, to some extent, it feels kind of weird that we're adding that many precompiles. They feel a bit like a performance band-aid, where if something is slow, you rather precompile for it, but it feels somewhat antithetical to the spirit of ZK-VMs, where, if anything, the idea is that you have, a circuit for a VM, and, you run things in that VM, and you don't write program-specific circuits. And so the challenge here is mainly that because you have so many precompiles, in the sense that you have several ZK-VMs which could be used on the L1, and all of these have multiple precompiles, you quickly get maybe 60, 100 precompiles that you might have to try to formally verify across all of these, which would be not necessarily impossible. Some of these precompiles are probably not too bad to verify. Some of these are harder, so the kind of Blanky-Street Ketchak, is quite hard, but it's also quite hard because there's just a lot of constraints, and enforcing all of these constraints in VS Code or any other kind of text editor is a performance bottleneck for that software. But progress has been made there as well, actually. So just the other day, someone was reporting that they were finished with their grant, which actually included formally verifying the Blanky-Street Ketchak Air. I haven't reviewed this yet. It'll be reviewed by the time the video comes out, but I think it's it feels safe to say that that's been done. And we're also looking into auto precompiles. So auto precompiles are quite nice. It's essentially kind of a nice compiler that looks at things that are expensive within the execution trace, and then automatically generates precompiles, for these repeated basic blocks of programs, which might be expensive for the prover otherwise. And so this is also going to be formally verified. The work on that hasn't started yet, but I think this is something where there's a nice tandem between trying to improve the performance of ZK-VMs, which auto precompiles are doing, and then supporting that with formal verification by introducing, these new compiler techniques that will generate auto precompiles, and trying to formally verify these as people want to adopt them, to make it easier for them to make that choice of adoption without having to worry about security. So I think that obviously it hasn't happened yet, like I said, but I think it'll be happening in the next couple of months, and that should hopefully be a nice thing to have. And at least I'm quite hopeful that we start to then just rely on auto precompiles and having that, kind of compiler verified rather than doing verification of manual precompiles forever, because this is just it's not necessarily impossible or intractable, but it's just a lot of, time consumed to be able to do that. So we'll see how that goes in the next few months, but it feels pretty positive. And then we'll also see obviously how ZK-VM design evolves and what that looks like. I think there's a lot of interesting conversations to have around that, from the point of view of formification or not, or just purely from the point of view of performance. And then that I think mostly covers things on the ZK-VM track. There are a couple other projects as well. We have a lean DSL for circuits called Clean, which also, for example, has a formally verified Ketchak precompile in it. And then we also have LLZK, which is this family of MLAR dialects for circuits, which should be quite fun, where that has had a good milestone recently, which is being able to represent all of the SP1 chips as LLZK programs. And then we're hoping to obviously integrate that with more ZK-VMs and more circuit DSLs. And then in the same time, this is also happening right now. It started happening, kind of a bit earlier in October. Hopefully we'll have support for backends, to Lean and Rock and other proof assistants. That should make it a bit easier to then verify any circuit that is compiled to LLZK. And then as well as obviously SMT backends where you can run PyCurves versus other SMT-based tools. And the idea here from a development perspective is also that instead of taking a circuit DSL and then you go and see form verification contractors and then they have to write an extraction from your DSL, to Lean or to SMT or to another proof assistant, you can have a compiler engineer that's been working on the DSL, integrate with LLZK, and then you get these verification backends for free. And then because of these verification backends as well, we'll be able to verify, optimization passes that happen, within the compiler. And that should provide, a nice high assurance toolchain that, gives you verification backends, but also gives you high assurance with respect to optimizations and allows you to potentially, implement some really sketchy looking optimizations, which is always a good thing to have when you're pushing performance. So that I think is also going to be developing, further in the next couple months. And we should start to see, kind of more use of that and integration of that with more circuit DSLs and ZK-VMs and any other kind of circuit framework, which should be good. Now onto the EVM track. With the EVM track, a lot of that is basically making sure that if you're running a guest program on a ZK-VM, which is basically an Ethereum client such as RES, which then has RVM as its internal EVM engine. The way that you then run that on the ZK-VM is that you have things like the RVM interpreter crate that translates the EVM bytecode to RISC-V, and you want to make sure that when you're actually executing, RISC-V code, it actually matches, the reference EVM bytecode that you had at the start, and so in particular that it, executes in a way that would be equivalent to the execution of a formal EVM specification. So we've had some work done on that. We've had some progress on that. We have some proofs that obviously for most of the EVM opcodes, that when they are interpreted to RISC-V via RVM interpreter, then the assembly that you get, executes in an equivalent way to a formal EVM specification. We have some annoying caveats, which is that obviously for opcodes which interact with the state, these proofs hold up to a kind of dummy implementation of a host and things like this. And then I think we still have probably a bit of work to do regarding gas safety and gas accounting, just because gas accounting turns out to be a bit of a mess to formalize, and then to go and verify. So this is kind of, I think, going well. The challenge there is mainly going to be that right now everyone is just running REST. There's only one client that people really run. So that means, the EVM of choice is just RVM. Now we've seen ETHREX obviously has been making progress. They should also be able to run on ZK-VMs right now. We also have, Guess and Nezamind and, other L1 clients which are going to integrate with ZK-VMs as well. So that's going to be a lot of different, EVM implementations to look at, and a lot of formations that's going to have to be done. And we'll have to, figure out some way to scale that out. Hopefully the tool chain is basically robust, and, we have the proofs right now that we have all done automatically via SMT solvers. And so if things are robust, maybe it's not that big a deal. But we have to wait to find out, if they're actually robust. We can only find this out empirically, unfortunately. So we'll see what happens with that. But hopefully it happens. Fingers crossed. And if not, obviously we'll have to put in some more work and make it robust. The other thing as well is obviously the EVM changes all the time. It changes more than once a year, hopefully twice a year if we manage to ship forks faster. And so it does have to be robust, to handle multiple clients on multiple ZK-VMs, because obviously the assembly that you get on different ZK-VMs is not the same. So even for RES on different ZK-VMs at the moment, they don't all use the same compile target. Even if they use the same RISC-V specification, they typically have a custom compile target, and so they don't all produce the same assembly, which is quite frustrating. So maybe there'll be some interaction with, we have some other efforts at DEF to try and, standardize some aspects of ZK-VMs, such as the RISC-V specification of choice and the choice of extensions, and then hopefully also, the RISC-V targets. So we have a PR that was opened a couple of days ago actually to upstream a RV64IM target for the Rust compiler as a tier 3 target. Hopefully we'll then get bumped to a tier 2 target so that it has better maintenance and better guarantees, and we'll see where that leads. But I think, again, we're trying to integrate with general development efforts and to make our lives a bit easier and hopefully then make life easier for everyone. And so lots to look forward to on that with respect to more Ethereum clients becoming viable guest programs for the ZK-VMs, as well as more ZK-VMs coming as well, and everyone maybe changing their RISC-V spec from RV32IM to RV64IM, or we've seen Jolt's RV64 iMac, and we'll see what happens there. So should be fun. And then the cryptography track, so that we cover everything. The cryptography track has, for now, primarily focused on developing executable specifications for the proof systems that we use. So the idea there is that if you look at the papers, you'll have some theorem that says, this construction satisfies round-by-round soundness with these security parameters. And then if you look at the code in Rust or something else, you do have the construction. You obviously don't have the theorem. And in relating, the Rust code to the constructions in paper is always a bit of a challenge. Because obviously, the paper might be written, obviously, one, it's not even pseudocode. It's written in, kind of very functional mathematics. The Rust code might look very different. The Rust code will also have implementations which aren't part of the paper, which might be known to the authors of the paper, but the paper might not be revised. The optimizations might just be implementation details that don't have an effect on the construction as is written down in the paper. And also because these are actually quite hard to implement, and it actually does take a lot of time to go from a paper to an implementation of a new proof system, there's a lot of centralization. So Plonky 3, for example, powers multiple ZK-VMs, whether that's, for potentially, the implementation of Fry and Plonky 3 itself, or whether that's just for, the backends in terms of, the implementation for field traits and things like this. And so this actually poses quite a bit of risk because we've seen, Plonky 3 had, a critical bug in Fry, for example. So we really want to have something where you have this theorem that says this construction satisfies round-by-round soundness, and that theorem is proven in lean and formally verified, and the construction is an actual executable specification that you can run. It'll run slowly at first, but you could at least do differential testing against it or differential fuzzing against it. And then you'll also be able to verify Rust implementations against this by extracting the Rust, obviously, to lean via a lean backend for hacks, which is a high assurance translation tool for Rust to proof assistance. And so the lean backend is, kind of completely new and fresh, and obviously also still being improved, but, functional at this point. There is a medium long-term plan to actually write a compiler in lean for these specifications so that we actually produce, like really fast code from lean through a, entirely formally verified compiler pipeline written in lean. But that's, maybe we can do another video next year.
Sure.
About that. But we've had some other cool milestones here. So we have a specification of Fry written in lean now. Not everything is proven yet. Obviously, there's kind of a big caveat, but we do actually have a specification of Fry. We do have computable polynomials in lean, so we can make this, fully executable, and we could kind of in principle run this specification. And then obviously, like I said, we have this extraction from Rust to lean, so we'll be able to compare Rust codes to lean. To the lean specification. We also have a specification for, for some check, and so Binius is also soon to be done. That includes Fry Binius, and then we'll have, whir and stir. We have some theorems that are formalized, but not yet the constructions. We'll also do Fiat Shamir is also coming, and then we can do kind of the BCS transform and all of this. And so I think, in the next year, what we'll start to see is one, verifying some Rust code from ZK-VMs against specifications that we have in lean, starting with, the field traits and working up to obviously Fry and some check and all of this, as well as the progress on specifications and getting, constructions for stir and whir, which are formally verified as well, getting, a reference Fiat Shamir implementation as well, because we've seen a lot of issues with Fiat Shamir, and obviously there are also theoretical issues with Fiat Shamir, but, just in terms of implementations, at least we've seen a lot of issues, and then that should give us, obviously, I think, one, greater confidence in the actual proof systems that we're running, specifically the verifiers. We want to be able to verify the verifiers to make sure there are no soundness bugs, similar to, being able to verify the circuits. And then, hopefully with the provers, we'll see what to do with that, because obviously people are, compiling things or using, custom handwritten CUDA kernels, and, that's a bit of a harder target to try and formally verify. But maybe we can get there. Later on, we'll see. But I think the kind of tagline, for all of this, or the short summary for all of this, is that, in terms of timelines, we're hoping to have, optional proving on DR1 after Amsterdam. So, sometime in 2026, ideally. And then we're hoping to have a mandatory proving maybe 2027, very early 2028. I think I'm quite optimistic about 2027. I think we can move quite fast, and all of that we basically want to support with form verification, such that at the point where this happens, we've got formally verified RISC-V circuits, formally verified precompiles or auto precompiles, at least for the the very key ones like Ketchak, which take up a lot of resources on ZK-VMs and which are heavily optimized, and then formally verified Rust verifiers. And so this should give you a lot of coverage to ensure soundness. and then combined with obviously, form verification for the guest program, should make sure that what you're proving is also what you think that you're proving, and maybe not something that the compiler has done a bit of tweaking to that you didn't intend. And so yeah, it should help the overall effort to ship ZK-VMs on the L1. And so there is a kind of productive goal to this. It's not purely ideological or out of fascination for verification. It's really ideally sort of we're able to actually ship these much faster, and hopefully that we also do all of this work in a sustainable way, so that when people change their circuits, change their proof system, rewrite their verifier, add new optimizations, we're able to handle this happening with respect to form verification without being a bottleneck in terms of developer time, and ideally actually being an accelerator by removing the reliance that there is currently on audits, which obviously take a long time, don't guarantee everything. And so that's also a goal, is really to help kind of performance and development, and all of this moving forward, so that we're able to ship faster, better code.
Yeah, that's great. I mean, like for a company like us that we believe that formal methods should be kind of like a quintessential step in kind of like shipping secure, better code bases, this is like music to our ears. So there is like a lot of to unpack from all of like the initiatives that are going on right now. But I want to be like a little bit selfish here and like move towards like LLZK, and like for people that don't know what LLZK is, like we at Veridise we're building like a lot of tools in the very early days of like ZK. And one problem that we noticed was that the space was very fragmented, like a lot of different DSLs, people using like different tech stacks. And when like the whole Ethereum Foundation initiative came up, we approached you to kind of like define an IR that kind of like unifies everything, and like as you mentioned earlier, instead of like going and implementing like the whole verification kind of like tool set for every different like DSL, you have like a compiler engineer who downloads like who like compiles like whatever tech stack people are using to write their own circuits to LLZK, and they get like all of this extra verification infrastructure or like compiler infrastructure for free. So I was curious to see like what people are currently building on LLZK. You touched a little bit on that like in your previous answer, and like what we should be expecting to see in LLZK in the future.
Yeah, so I think LLZK is quite interesting, because I think it's a good example of trying to embed formal methods and formal verification into the stack, as a default, and not as something that you then have to add on in a kind of ad hoc way, so to speak. So obviously, yeah, Veridise, you did the original development, and I think when that announcement of the whole verified ZK-VM project came out, obviously I did have in mind, we should do an IR or something, and so I was very happy to see the proposal, and I think it's gone obviously very well so far. I think the interesting things to pull out of LZK are, one, I think, is actually the use of MLIR, because MLIR was created in the kind of AI world, because it was trying to solve this problem of try to unify compiler tool chains that were used in AI, which were very varied because people also had heterogeneous hardware. And they looked at this, and so they had all these different compilers that couldn't really talk to each other. And you can also look at like LLVM. And right now you have like LLVM as this kind of like monolithic backend that people compile down to, and then you can then go to x86 or ARM or RISC-V or all of this, and so it obviously has a purpose. But anytime someone wants to do something domain specific or even language specific, they have to implement their own IR on top of this, right? And so fundamentally, MLR comes out of the idea that if people do want to do these domain specific implementations of compilers and optimizations for domain specific things, then what you really need to work out is actually just not a specific IR or a singular IR in any sense. What you want to work out is actually just a nice way of defining IRs and then lowering from one IR to the other. And you see this with circuits. Circuits are like a very good example of this, because circuits, in terms of what they use relative to what a program can use in LLVM, is very, very narrow. You have, it's a bunch of polynomial constraints over a field. And so you don't need everything that could be done in LLVM. You're going to need, some model arithmetic, some differential polynomials, field arithmetic, things of that kind. But you do want to then actually optimize these as much as you possibly can, because obviously that's where performance comes from, is having, fewer constraints of lower degree. And if you want to do optimization passes for these, then it helps a lot to actually have an IR that maintains a lot of the structure of those constraints, so that you're not looking at something that is, incredibly low level, that doesn't really look like a constraint anymore, that just lost a lot of the structure. And for example, you could think of, if you look at Keccak. Keccak is a hash function where you have different permutations and then they are composed into rounds. Ideally, when you're writing your circuit for Keccak, you optimize the constraints, and you can see this if you want to go and look at the Plonky 3 Keccak. You have a bunch of optimizations which are basically looking at, part of a permutation or a permutation in a whole, and thinking, okay, the naive way of having these constraints you can actually replace by, one constraint or set of constraints. And there's one example, for example, which is replacing a bunch of singular XOR constraints with one algebraic constraint, which is high degree, but it's one constraint instead of four. And so, you have performance gains there. And, if you want to apply these kind of optimizations, ideally not by hand, because when you're doing these things by hand, it can be hard to reason about. You can introduce bugs. It also takes time, maybe. It also, depends on the engineer being able to do so, and you want to have that done by your compiler instead. You do need to have that higher level of structure of, okay, what's the permutation, in that code, so that you can actually optimize this. And for that, it helps to have dialects that can be lower level or higher level, and a way of lowering, through these dialects until you reach, an actual constraint that is emitted. So I think it makes a lot of sense for such applications to use, things like MLIR. And I think it simplifies a lot of things. So it means you can have different front ends, which actually, essentially kind of re-implement, a kind of a language in, in MLIR that makes it very easy, to integrate with. And obviously you've been doing some of that work with like the Circom front end for LLZK. So hopefully it's, it's easy to integrate with. You get this nice set of constrained dialects that you can then do optimization passes for. And then because these dialects are also quite constrained, it becomes much easier to also formally verify them, because the range of things that you need to formally verify is much more limited. And then if you need to do another optimization that looks sketchy in that dialect, you can create a new dialect, you load to that in a representation which is, kind of well formed for that optimization. And that again makes it much easier to formally verify. And then it also gives you modularity. You don't have to go through every dialect. You can pick and choose the dialects you're going to use. You can obviously go through different backends for different styles of rasterization. You could have different backends for witness generation. If you wanted to have, an LLVM backend for CPU, you could also plug in a GPU backend if you wanted to run things on GPU and things like this. And I think one thing that obviously came up when we were chatting initially is that at the same time I was reading a lot of papers about Lean MLIR, which is this project to basically have interoperability between Lean and MLIR. And I thought that was quite exciting. So, this is a great way to obviously try to formally verify these things. And so I was quite enthusiastic as well about MLIR with respect to this, that it seemed like, it's hit that middle ground of, you can actually build good compilers that offer good performance, good developer experience and all of this. And it comes as a framework to also verify things. And then there's also obviously, another thing you can do is, because you have a lot of flexibility in how you, implement dialects in MLIR, you can have SMT dialects. And so you can lower, your constraints to an SMT dialect that is then, fed to an SMT solver, instead of having this, again, kind of, ad hoc encoding of, your circuit DSL, kind of high level language, or, reading off of the AST and trying to encode that into SMT. And a lot of things just become much, much nicer by having the flexibility to actually implement this properly in a kind of, uniform way, that everything is like big family of dialects. It just happens that you have some dialects which are, actual intended for SMT, other dialects which you intend to kind of lower for witness generation, other dialects which you intend to lower to emit constraints, and that you can also separate these things cleanly. So even in LZK, you have the compute tags, the constraint tags, and so you can handle both of these. You can mix them up, you can separate them, you can feed them to different dialects. You can do then optimizations to one or the other separately. A lot of things just work quite nicely with that. I mean, we should re-implement everything in MLIR, really, but that's a personal opinion.
Yeah.
But I think that's meant that it's been, I think, quite an exciting project, because it means that we, I think, are able to have support for form verification into something that is an otherwise good piece of software, which has been a problem with a lot of other compiler verification efforts before. So, the other big compiler verification efforts that happened is things like CompCert, which took some, insane amount of human years to complete. However many people did their PhDs on that, and that's for the C99 specification. It's obviously a compiler where the licensing is kind of can be a bit annoying, and we obviously performance is also actually not as good as obviously if you go through your regular competition pipeline. You have things like Certicock, obviously, which also for some certified compilers, and then you have many other papers in the academic literature which are a verified compiler for this kind of language that is an academic thing that people don't use and things like this. And so I think it was important to settle on something that was a compiler framework that people could use, that we know can be used for applications with ZK-VMs, where if you want something like GPU backends or something like this, that's obviously MLIR kind of comes from that in the AI world, and where we're able to just write fairly minimal compilers for exactly what we want, with all of the ZK stuff, which is basically kind of field arithmetic, polynomials, constraints, and for the provers obviously it's a lot of this as well. So yeah, it's been good fun, and so we have several kind of ongoing projects as well related to that. So obviously we have Veridise. You've been developing it from the start, and now we're starting to see, now that it's kind of grown and matured a bit, and like I said earlier, you're able to have all of the SP1 chips represented there. Now we've also got some work starting on this lean MLIR application to LLZK, and therefore getting LLZK semantics into lean. I think obviously the work on integrating with system solvers will start both with you guys as well as obviously the team behind Cyber at UCM. We're also looking at it, and then hopefully also we start being able to verify optimization passes, adding more optimizations, and all of this, and having obviously starting to support more DSLs as well. I think it's something that isn't going too much now beyond the current SP1 thing, Circom, and I guess there was a prototype for Zergin early on, but I think we'll start to see more integration with that, and even actually for Clean, which is the circuit DSL in Lean. I think we've been looking at that as well, and hopefully we can form a kind of convincing argument of you have this DSL in Lean where you're able to formally verify your circuits as they're written, but maybe it can be a bit of a hassle to obviously try to then do verified optimizations and all of this. And so maybe this is where, even for something that is already formally verified at the source in Lean, maybe we can still actually offer something which is verified optimization passes, and maybe faster witness generation than the Lean compiler itself would offer. And so I think if we can offer something compelling to a DSL which already supports formally verifying things at the source, I think then obviously hopefully that's a very convincing argument that we have a lot to offer to every other DSL as well.
Yeah, that's great. And then just for people who want to know, where they can find all of these things, I think it's worth mentioning that we're gonna be hosting all of these projects that you mentioned that are already happening, or any future projects in their own LLZK organization, and we'll put relevant links wherever people are watching that, so they can access and then go contribute and make sure we have a very robust MLIR ecosystem.
Yep. Yeah, I see. So I think this is actually very important, because it's the point of this is to it's extensible, and so it's also quite easy to prototype things. So I want to maybe highlight that obviously a lot of MLIR you see written in C++, for performance reasons, but you can in principle write MLIR in any language. And so if you want to prototype things, you can do so in Python using XDSL. I'm not sure when this will come out, but there will be a paper coming out soon on actually asymptotically fast MLIR data structures in Lean, if you just want to write MLIR compilers in Lean. And so I think this is one of the nice things, that hopefully people do take a look at it and see it as an actual framework, for compilers that we can use, and not just as kind of a specific pet project of ours, or Veridise is something, and that people come and try to extend it, try to make it better, try to make it work. For their use case, it might be that you only need to add one dialect, and then you get a lot out of it because of the other existing dialects. And it might be that you can prototype something in Python very quickly and see if it works for you.
That's great. Okay, taking a step back and looking a little bit into the future for EVM and Ethereum in general, what do you think the roles of ZK-VMs will be, and in the general ecosystem? Will be interacting with ZK-VMs, or will still be interacting with the L1 directly?
Yeah, I think ZK-VMs are going to change a lot. So the biggest change in the short term will obviously be this idea of, verifying proofs instead of doing re-execution on the L1. The biggest practical difference that will make is obviously being able to increase the gas limits, by a lot. Because of parallelization, within the ZK-VMs for proofs, in principle, we should be able to increase the gas limit, just by a lot, as long as there's, a cap on the gas consumption of a single transaction, which there will be, obviously coming very soon with the next fork. And so I think that should be a very big boost. We'll be able to handle, more throughputs, from the L2s. Obviously, that means cheaper transactions as well. So that'll be, I think, a huge difference. I think it also changes what the execution layer looks like as a result. So I think we'll see greater changes in the long run because of that. We'll see also some impact on the consensus layer. So people have seen, Lean Ethereum, which is this kind of rebranded beam chain because of a cease and desist. For that, again, we can have, maybe ZK-VMs, we can verify the correctness of the state transition function, or ZK-VMs, which are used for aggregating the new post-quantum signatures that the EF has been working on. And so people can go and look at this Lean Ethereum and Lean VM project, which is part of, this whole idea of how do we use ZK-VMs and ZK in general, within Ethereum. So that'll be another big thing, which is hopefully actually, once the complexity of the ZK-VMs is also tamed, then suddenly we can probably reduce the complexity of many, many other things, because you just reduce things to, okay, let's prove, this guest program. And I think this is one of the nice things, is this kind of, general purpose feature of ZK-VMs, that you're just proving a guest program, is that then you don't need to do this, we're going to prove this, so we have to write a circuit specific for that, and then if that changes, we need to rewrite a circuit. The ZK-VM can obviously be stable or just independently developed from what it's actually proving. So that makes a big difference. We're also, I think, going to see what happens when it comes to then, once ZK-VMs are there and ZK-VMs are seen as, this kind of scaling solution, which I think, they are, just obviously we're not, using them to their full potential yet, and they're not fully deployed yet. I think we'll start to see other changes in the design space of Ethereum, and some of that is already obviously part of, Lean Ethereum and that whole project. But for example, one big thing is right now we're, interpreting EVM bytecode to RISC-V, because what we're finally improving is RISC-V. What does this mean, for the EVM? What does this mean for, all of the EVM clients, or all of these kind of L1 Ethereum clients for the execution layer? I think that there's a lot of interesting kind of open questions there. There's a lot of interesting questions as well about, what the best ISA is, whether RISC-V is the way to go. How do you then get, these other Ethereum clients to compile to RISC-V, whether, there was other ISAs like Cairo, obviously Valida. I guess Valida is maybe less alive now. But, there are other options than RISC-V. I think, people are looking into trade-offs. I think, I'm fairly confident RISC-V will probably stick around. There's also, do you need a canonical ISA? Can you support multiple ISAs? And then people just, compete to do the best, fastest ISA that they can do, in the same way that people compete in other performance metrics. Maybe the client teams become ISA developers, right an ISA instead of a client. So I think, a lot of things will change. I think once we have ZK-VMs, integrated in the L1, and we start to see kind of the full potential in action that we can empirically measure. Beyond, obviously, right now we have ETH proofs. It's showing that we can do real-time proving, but it's, there is going to still be a step from ETH proofs to having, ZK-VMs on the L1, and potentially, obviously, doing some redundancy of, proving multiple guest programs as multiple ZK-VMs for every block, or something like this, where we'll have to relate that against the assurances we can provide in terms of security. And then also, obviously, once you, no longer kind of strictly need the EVM in the sense that you're proving RISC-V code, that opens up the door to also developing smart contracts in things other than RISC-V. And so you have things like, R55, which was a way to write raw smart contracts. That's something where maybe people can just start, write raw smart contracts, compile to RISC-V, kind of do bypass the EVM. How does that integrate with the EVM? Does the EVM become, maybe an IR for Solidity or something like this? I think these are fairly open questions. People will have, very different opinions on this. Some people, I think, view the EVM as, one of the big selling points of Ethereum, because there's a big developer ecosystem associated with EVM, especially compared to, remember other alternative L1s that have other VM models where maybe there are just fewer developers because it hasn't been there for as long. The developer experience may not be as good, or there's a lot of different kind of pros and cons to all of this. So I think, mainly we'll just see probably a lot of lively discussion.
Yes. So do you see like maybe a day where like, the EVM itself like changes an ISA, or like, goes like to risk zero, or like, whatever like else wins the battle?
I think it's hard to say. So one, I think there always has to be like some EVM which is there for kind of backwards compatibility with things that already exist, right? I don't think we can kind of decide to break everything that already exists on Ethereum. That would be a pretty bad move. But I think that if we at least have the option of letting people not go through Solidity and EVM if they don't want to, that seems like a win. And it seems like something that could be handled alongside letting people use the EVM if they want to. And then, maybe maybe that has an impact on transaction pricing, because maybe EVM transactions or things that go through EVM might be more expensive because there's some overhead from interpreting, that EVM bytecode to RISC-V. Maybe people write like a really good EVM to RISC-V compiler, and a lot of that overhead goes away, and you just stick with EVM as a result. Maybe people come up with a custom ZK-friendly ISA from which you can compile the EVM, very efficiently. I think the design space is quite big. I think the design space is quite unexplored, and we'll have to see what happens. I think personally for me, I think something that's also maybe undervalued is that there's a lot of discussion around the EVM and around RISC-V and around, alternatives to RISC-V instead of ISAs and things like this. It feels to me like the actual key points are not necessarily the like final ISA of the ZK-VM, but rather the compiler toolchain. That to get you down to that ISA. It feels like obviously you can write a more ZK friendly ISA. There are trade-offs to this. There are trade-offs to Cairo, for example, where Cairo obviously works really, really well for Cairo, and it works really, really well for their use case. But their use case is not necessarily proving Ethereum L1 blocks, and so different things will work for different people. And things like write once memory come with potential gains when you're trying to get fewer constraints. But maybe other implementation issues when you try to run other languages. And so we've seen, Starkware was looking at, should they do a RISC-V ZK-VM to support Rust, because supporting Rust on Cairo would be tricky, and things like this. And so I think there's a space for everyone to do a lot of different things. A lot of people are doing like fantastic work. So Cairo was fantastic. What Veridise was doing was fantastic, even if it didn't fully pan out. And then all of the RISC-V stuff has also been fantastic. And all of the RISC-V stuff, I think, there are a lot of compiler things that you can probably do, to optimize things, for RISC-V, without having to get rid of RISC-V, or without having to make RISC-V more ZK friendly. You could obviously write, RISC-V is extendable. You could definitely, when people have precompiles or even auto precompiles, you can, a lot of the ways that people do precompiles right now, I think, traditionally you have like a syscall at the RISC-V level. But you can look at some ZK-VM designs like OpenVM, where there's no necessary central notion of CPU or canonical ISA. Everything is treated as an extension. So RISC-V itself, you can kind of treat as an extension, and in the precompiles, you can treat as extensions. You could have a kind of, core EVM thing that you treat as a RISC-V extension. And a lot of this depends on having good compiler toolchains that can do domain-specific optimizations for what you want to do, and which can also be kind of a good way to integrate, accelerators and things like this. There are a lot of interesting papers about this in the kind of literature for people who, don't care about blockchains, but do kind of things with MLIR and, kind of things of, academic work of that kind, where I think, you can have, compile infrastructure that can handle compiling down to RISC-V plus a custom extension, which is basically an accelerator, and which makes things, better integrated than if you have a kind of, completely separate, like hardware accelerator or something. So I think that will also make a big difference in how we view things moving forward, is when, people start looking a bit more at the compilers, which people are doing, like auto precompiles is something that came out of that, right? Instead of looking at, let's write more manual precompiles, let's keep the ZK-VM as is, have these syscalls, write another manual precompile. Let's look at the compiler. Let's look at how do we get a better compiler. that can do some profiling and do some runtime analysis and, come up with optimizations there, for ZK-VMs, which are domain specific, right? It's still basically just generating better constraints. That's only, I think, the start of it. And we'll start to see, people develop, like more dialects or, specific kind of IRs or dialects within, MLIR or other compiler frameworks. And I think that'll hopefully take up more resources and just kind of, this discussion of let's do a customized and things like this, where, there is kind of, if you, at least I feel like if you want, Ethereum to be, a platform for general purpose computation, you are going to need a nice for general purpose computation. And, maybe you're saying, okay, within an Ethereum block, do you really have general purpose computation? Maybe not. People will argue that, and then we'll see what comes out. I don't think, I'm not the person who will have the final word on this. I don't think anyone will have the final word on this. It'll be, the community and ACD and, trade-offs. But I think it's on all of us to try to illustrate what these trade-offs are and have an informed discussion, before committing to anything.
Yeah. I mean, and that's the ways work anyway in Ethereum. So, that's good. All right. Yeah, I think there is like a lot of food for thought. I think, we can wrap this conversation for now and then maybe pick it up sometime in the future. Thank you a lot for your time today. And thank you for doing this great work with Ethereum Foundation.
Yeah, thank you for having me. And thanks for everything that Veridise has contributed.